So last time we talked about homomorphism. We defined the notion of a homomorphism between groups. This is an essential, as I said, an essential tool in math to be able to compare different structures that you're working with, abstract structures. So homomorphism is that link for groups. And we use the same term when we talk about other algebraic structures, but we'll have to redefine them in those contexts. So let's recall what this means. So a homomorphism G, one group G to another group G prime function. A function of sets that sends elements of G to G prime, satisfying one key equation. That B of say AB, B of A. You'll notice here when we're combining them, we're using the composition in G, whereas here when we're combining them, we're using the composition in G prime. Linking those two different ways of composing elements. So let's talk some examples. I said one example sort of hurriedly class, and that was the determinant. Example one. And GLN R, of course, replace R with other numbers, types of numbers, to R times. We'll call that just denotes all real numbers except 0 and multiplications. That's one homomorphism. But really, I shouldn't have started there. That's a complicated. I mean, sure, we've seen that. There's a lot of more elementary ones that we could have thought about. I want to convince you that you've been dealing with these your whole mathematical life. Okay. So one of them is just multiplication. And we could just say, you can say by any number, but let's say, well, yeah, any number really. Let's say by 2. And let's call this, say that's phi. And then phi is going to send, again, you can do things, but we could say R addition. Why is that? So what's the law? What is this? And saying, well, this is really just a distributive property, right? We're saying that if I add 2 elements, multiply by 2, same thing. Other arithmetic one that you've been dealing with since probably middle school or so is exponential. So exponential function will take, say, a real value with addition to a real number. B, so this sends a number, say A, sends it to E of A. I mean, I don't know if you're familiar. So I think if you've done any computer programming, it's exponential. Often we write functions E to the A. But mathematicians will write A or something. Okay. And why is this true? Well, if I take X of A plus B, I'm defining it this way. E to the A plus B. That's E to the A times E to the B. Right? Just X A B. Now, of course, right, you have to remember what the operations are in your groups. I mean, they look the same set, except here you course lose 0, but the operation here is the addition operation. The operation here is the multiplication Exponential is a homomorphism. In fact, it's an isomorphism. Inverse law. Also, you don't like arithmetic stuff. Well, there is a group of functions. You can make functions from reals to reals a group, right? Under addition. So let's call this, and I'll write this as proper terminology. Group. This is the function, I'll say is the group of all differentiable functions from R reals to R. So calculus 1, you learn about these functions, and you can add them, right? You have two functions, you know how to add the two functions, just add, put an input, just add the values of the two different functions. Okay. And of course, that actually forms a group. There's the constant function 0. That acts as an identity. And if you have a function, you can take its negative. And when you add a function, like you get 0, so it has additive inverses. This is a nice group under addition. And indeed, if I look at the derivative, this is a homomorphism. Although it goes to a group, it's a slightly different group. The derivative of a differentiable function need not be differentiable. So this is the set of all continuous functions. So C1 actually denotes differentiable for continuous derivative. And the reason for this, why is this a homomorphism? Well, you guys all learned this in Calc 1. One of the first things you learned. It says that if I take the derivative of the sum of the derivatives. Precisely the defined. Homomorphism. Okay, but derivatives are easy and you like integrating. I know you guys love integrating. And integration is also, definite integral is also a homomorphism. I can take continuous functions. Let's take a definite integral. I'll return real number under addition. And again, this is a homomorphism precisely because of that, one of those early properties you learn about is that if I integrate here, I'll just be a little bit shorthand here. Integral of a sum is the sum of the integrals. This is what it means to be a homomorphism here in this context. Okay. So hopefully these examples are convincing that this is something you see everywhere in math. And so formalizing it and trying to understand it, and learning a little bit about it can be very helpful. It's one of the things abstract math does best. Okay, so these are maybe more familiar homomorphisms, but then, there's some that we just learned as well. Take a symmetric group on n letters, right? This is just a group of permutations of numbers 1 through, I said letters, but 1, 2, 3 to n. The set of permutations is a group, and we learned that we could go from here. In fact, there's 2 homomorphisms that we defined, but we'll just talk about one of them, maybe the composition of them. We learned about homomorphism from 1 to -1, plus or minus 1, multiplication. And this is just the sign. We learned about the sign of a permutation. This is a homomorphism. And the reason is because this homomorphism, as I was saying, this actually factors through two homomorphisms. One is you take a permutation and you assign its permutation matrix. There was a homomorphism that we defined that said, okay, take a permutation, give a permutation matrix. And when we looked at that, there was a theorem in that section which said that this was actually compatible with, if you compose the permutations, that went to the product of permutation matrices. That's precisely saying that that's a homomorphism. That assignment is a homomorphism. Here you have a homomorphism. Determinant we know is a homomorphism. You can compose homomorphisms and get homomorphisms. That's an elementary kind of exercise to show that that holds. So indeed, sign is a homomorphism. Useful, very useful one. Now, I think many of these, if not all of them, I'm trying to see, are actually surjective or onto maps, the ones that I've given. Maybe it's with the exception of this. That's not surjective. But of course, they don't have to be onto homomorphisms. You could have an inclusion. So for another example that you could consider is you could take all even integers under addition. You can just include it into all integers. You know, you're not really doing anything. You're just looking at it as a subgroup. And so therefore, this will satisfy the definition. The homomorphisms aren't always just kind of going onto something. They can also be included into it. All right. How do you feel? Yeah, go ahead.
Differentiation function.
Well, that's a good question. So this has an inverse, which is right here. Well, the inverse of this is by the fundamental theorem of calculus. And you can integrate from say 0 to x. And if you integrate and then differentiate by fundamental theorem of calculus. You're saying.
But if it's over a set,
And then you integrate, you lose the constant.
but if over the
You can also put a no, that's you're saying of it, it's not injective, it's surjective, it's not injective. Yeah. So the comment is this, so I was saying that all of these are onto, which means any function over here I can integrate and I'll get something that's sent to it. So this is not so this is actually a left inverse, but not a right inverse. So you're right. This is not injective. Derivative is not injective because if you have a constant, it goes to 0. So all constants go to 0. In fact, there is a notion of the lack of injectivity, which I'm going to jump to because you brought it up, but we'll return to it in a moment. So there's a definition. If I have a homomorphism, you can define a subgroup of G just from this homomorphism. Set all elements of G such that phi of G is equal to the identity of G prime. This is called the kernel of phi. It's noted kernel, not my name, of an R. Phi. What you're asking about is the kernel of this differentiation. The kernel of differentiation consists of all constant functions. The set of all functions that goes to the additive identity 0, and that is non-trivial.
What is that thing on the right there? The 5G.
5G equaling 1 of G primes. There's an identity in here. This is a group. So 1 of G prime is an identity.
Okay, so it's just
So it's the set of all of the elements in G that are sent to that identity.
Okay.
Yes.
Isn't that also like the same thing as like null space in the matrix?
If you're talking, yeah, if you're looking at like say column or row vectors, and you have matrix multiplication, that will define a homomorphism of the additive group of say column vectors. And yeah, then that's right. You can talk about the null space of that homomorphism, and you can equate that null space to a kernel. We'll get into that actually a little bit in the next chapter. Yeah, and kernels again. There's sort of how many people do some programming? Okay, because I kind of reference it sometimes. It's not necessary. There's something in computer programming called operator overloading,
Yeah.
right? Where you want to use the same symbol in different contexts,
Yeah.
right? And so there's a lot of operator overloading in math. We use kernel for group homomorphisms, ring homomorphisms, homomorphisms between vector spaces. We use homomorphisms in all of these different contexts too. So it means, technically it's a different thing, but there's a lot of there's a lot of similarity between all these concepts. So we kind of use the same terminology. All right. So let's look at it. So now we have some set of examples that we can think about. Let's do some general facts or propositions about these homomorphisms. So I have a couple of propositions. Excuse me, from Arden. I want to look at. This is a fairly elementary proposition. It's just saying that this property, this defining property that we have. Sorry, just rewrite it. This defining property phi of AB equaling phi of A, phi of B. This guy, we don't need to just have two elements that we compose. We can compose as many as we want. And what sort of phi, in a sense, distributes, if you will, through as many products as we want. We know that the identity will always go to the identity. And we know that inverses will go to inverses. So if we were to prove this, and maybe I'll prove a couple of these statements, let's just get a sense of how such a proof would go. So what do people think for A? What would be a good way of proving A? Thank you. Great. Absolutely. So you're noticing there's a parameter in this statement, discrete, parameter K, and we want to use induction, and so proof by induction, for K greater than or equal to 2. I mean, of course, for K equaling 1, this is sort of a silly statement. Okay, so the base case is really the defining property of the homomorphism. So we don't need to prove that, we've defined it, and that's by definition. So let's assume it's true. Assume it's true for K. Assume A holds for K. We want to prove it for K plus 1. But then all we have to do is we take a look at phi of A1 to AK plus 1. And we use, associativity. This is phi of A1 up through AK times AK plus 1. We can prove these however we want by associativity. Now we have the defining property of homomorphisms. We have two elements, namely the product of all of these and AK plus 1. So we can take this first product, figure out AK plus 1. This is by definition. But then we have the induction hypothesis. Right? The induction hypothesis tells us that this factor on the left can be indeed written as the product of VA1 up to VAK. And if you put parentheses here, maybe we should say by associativity here, sorry. And then this is by induction hypothesis. And then again, by associativity, we can just forget about the parentheses. So this is a very straightforward induction proof, right? But it's, again, for those that are sort of still feeling their way through induction type proofs, it's useful to maybe look at this kind of thing. So for B, let's do B2 and we'll feel good about ourselves. So what do people think for B? Let's say that the identity goes to the identity. So identity, this is a trick that you kind of get used to when you start to learn, get more comfortable with groups, which is that the identity is sort of the only element that when I compose it with itself, I get the identity. Right? And that comes from the fact that I can cancel it in a sense on both sides. So it's the only element that will do that. So when you know that about the identity, you can just use that, right? And so let's take a look. So B of 1G is equal to, well, as I said, 1G is 1G times 1G. I can times it by itself, and I get it. But now I use the homomorphism property. So now I have an equation that's sort of in G prime. This is some element of G prime, and it equals itself times itself. There's only one element in G prime that will do that, and that's 1G. So in other words, I can, if you want, you can multiply both sides. I mean, you can use cancellation here. There's an earlier proposition that we had that says that this means that this is, or you can multiply by the inverse of this. If you do that, so let's just do that for clarity. Whatever that is, it has an inverse. G prime is a group. We get that 1 of G prime equals phi of 1G inverse and phi of 1G. Now here, this phi of 1G is equal to phi of 1G squared. And then we can just use associativity and see that this is equal to phi of 1G. Yes.
So that P, like the 1G doesn't even denote the actual number 1, right? It's just the identity.
It is the identity for G. Yes. So when you're dealing with multiple groups, you don't want to use 1 as the identity because you want to denote which group you're talking about. So 1 sub G denotes the identity of G. 1 sub G prime denotes the identity. I mean, again, like, so in other words, if I look back up here at this example here, right, the 1s of R plus, this is 0 as a number. It's the identity of additive reals. This notation. Like 1s of R times, this is 1 as a number. If I take e to the 0, what do I get?
1.
1.
Oh.
Sending the identity of R plus to the identity of R times. Okay. Similarly, if I took the identity of these guys, this would be the constant function 0. Constant function 0. Identity of Sn, 1s of Sn, that's the isomorph, that's the function that sends the numbers 1 through n to just themselves. It's a function. So we're dealing with groups. One just denotes that unique identity. So G. Okay, I will prove the part C. You guys can look at that yourself. One thing we can get from this, though, is the following observation. So let's observe. Kernel of phi is a subgroup. Here phi is a homomorphism from G to G prime. Because what do you need to verify? You need to verify three things to say something's a subgroup, right? Identity is in it. One. Well, certainly one of G, as we just saw, phi of 1G, this is equal to 1G prime. So by the kernel is the set of all the elements sent with identity. So the identity is sent with identity. That's by part B, we just proved that. You show that inverses are in it. So, well, if A is in it, A is an element of the kernel of B, then phi of A is equal to 1 of G prime. That's kernel set of elements sent to identity. So phi of A inverse, well, that if you look back at part C, part C says phi of A inverse is equal to phi of A inverse. Phi of A is 1 sub G prime, and the inverse of the identity is the identity. So that means that A inverse is also G prime. And then finally, what's the third thing we need to show if we want to show that something is a subgroup of some subset is a subgroup? Closure means I take two elements in that set, I combine them, that it's still in that set. So let's see that. So if I have two elements, A and B in the kernel of B, I take their product and I put it into phi. Let's see what happens. Phi of A times B. Now we just use the defining property. That's phi of A times phi of B. Homomorphism, so I can do that. And each of these, because they're in the kernel, the sense of identity, G prime. So this is 1 of G prime times itself. Just 1 of G. So, so a kernel is not just a subset. Kernel is a subgroup. In fact, we'll see it's a special kind of subgroup called a normal subgroup. And these subgroups are very useful to try to understand homomorphisms and how you relate groups. Okay. So let's take a look and see some of these kernels. I gave one example, but maybe we should look at a few more and see. So let's illustrate kernels here. Kernel of the determinant map actually has its own name. It's so useful. It's called the special linear group. Special linear group. Special. Yeah. I'm sorry. Kernel of a multiplication by 2 is 0. You know, what gets sent to the additive identity? What gets sent to 0 when I multiply by 2? Well, only 0. So this is just 0. Kernel of the exponential map is also 0. Right? The only thing, if I take x of something and I get 1, for e to the a equaling 1, that means a is 0. So this is again 0. So let me ask people the question, what do people know what happens or anything about what happens if I replaced R in both cases here with a complex number? Well, okay, Euler's formula will tell me something about it. That's good. But yeah, that's very good observation. So there is something called Euler's formula, which is related to this. But do people know the geometry of that? That's true too. Yeah, that's right. Well, it's sort of like rotation is a good way of saying it. I don't know. It sort of takes the complex plane and it wraps around itself. Wrapping. But anyway, if I did that, then there would be a kernel here. The kernel would be 2 pi I times the integers. But in this case, for just the reals, you just get 0. Pretty interesting. As we saw a moment ago, the kernel here, in this case, is just constant functions. Several constant functions. Integration is has what? What do you think for the kernel? Let's do this. Let's do this. That way we'll fix A and B. That way you can kind of tell me an example of something in the kernel. So yeah, the set of all continuous odd functions is in the kernel. It's not the only. I mean, you don't have to be odd. If you integrate an odd function from -1 to 1, what do you get? 0. You get 0. You get the additive identity 3. Right, because you get cancellation. This integration is signed area. One side is the negative, the other. So this is 0. So the kernel will just be all functions that have integrals here. All functions with signed area 0. But it'll be bigger than that. Signed area. I don't know what else to say. Kernel here is what we call even permutations. And this also has a name. Very famous group. This is called AN. It's called the alternating group. See, I don't know. We're probably not going to prove the simplicity of it, but it's a very famous group. And of course, if you have an inclusion and then a one-to-one map, the kernel has to be just the identity, because you can't have two elements for a one-to-one map that are sent to the same element. Yes, please. Which one?
Just the top 3 exactly do you mean by even permutation?
An even permutation was defined to be a permutation with sign 1.
Okay.
That's just, and we call the other ones odd permutation. It's common, it's language. Good. All right. So now we're going to define a couple more subsets, and I'm going to talk a little bit about isomorphism. So there's an important concept which is called a left or right coset. So of a group. So let's let G be a group, and we have a and let's say we have a subgroup, and H a subgroup, which we denote by H equal to. Which is a subgroup. The left coset coset. Is a set of the type subset of G. A times H. So it's a set of all multiples of H on the left by some element of the group. This is how we define it. The subset of G, or some element. G. Now, this is not, bold letters, not a subgroup. Okay. It's a subset, not a subgroup. So if A happens to be in H, then it will be a subgroup. But you shouldn't ever be thinking of left cosets as subgroups, just subsets. Okay. And a right coset. So a right coset, obviously, it's just you multiply on the right. Just of the type H. We're very sensitive nowadays, where we become much more attuned to our universe, and we realize that these things are not necessarily the same thing, right? Because of the lack of commutativity in groups. Okay. So the reason I want to define that is I want to look at another proposition, and I'm not going to spend long on it. We can just look at maybe one of the many implications, but it's one of those things we'll come back to. So I'd like people to read about it. The proposition 2.58. But just characterizes elements that get sent to the same element. So if you're interested in a homomorphism and you want to know about its properties, I mean, it's a function first, so we can ask about like its lack of injectivity, right? And injective says that if I take two elements from G, they should go to two different elements. So if that fails, and it generally will fail, we can ask, okay, well, what if they go to the same element? What can we say about these two elements of G? And this is a proposition that tells you a lot of things you can say about such a situation. It says, okay, if we have these A and B, and they're sent to the same element, well, if we have A and B, and they're elements of G, and K is the kernel of phi, then there are a bunch of equivalent properties. So here we've got the following are equivalent. They're sent to the same element. If I take this guy, A inverse B, it's in the kernel of phi. We got a relationship that B is in the coset A times the kernel, and that the cosets B times the kernel and A times the kernel are equal. These are all equivalent properties. Again, I won't prove them all, but let's just prove the first implication. Let's say phi of A equals phi of B. Well, then one thing we can do is we can multiply both sides on the left, say, with phi of A inverse. We can say 1 times G prime is equal to phi of A inverse times phi of B, multiplying on the left. But now we have this, we can take inverses in. We've gotten that from the last lemma that we had. Now we have the defining property that this is phi of A inverse B. Products. And so that implies A inverse B by the defining property of the kernel is in K, which again, this is the kernel. This is so this is this implication, and you can read through the book. You can read through the book to see that that's implied, that's implied. Or you can do it yourself. I would encourage people to try to sit down and try to prove these implications. They're not hard, but it takes a little time. Okay. But from this, there's a nice corollary, which is very important and often forgotten, even for graduate students. I teach grad algebra sometimes, and it comes up in a lot of theorems. And something you shouldn't forget, it's a very helpful thing to remember, which is that phi, if I have a homomorphism, phi is a homomorphism from one group to another, then it is injective, which is again one-to-one. If and only if the kernel of it is the identity. It consists of one element. That again is to say, well, look at these two things. If it's injective, then this is true if and only if A equals B, which would say that this has to be identity. A inverse B is identity. And vice versa. So I'll let you know. Okay, there's one last theorem I want for saying a few words about isomorphisms. I'm not going to spend a lot of time on 2.6. I'm just going to give you guys a picture and then move on to the next class. But there is a definition that's very important, and I mentioned it a moment ago, that of a normal subgroup. Let me just define it. Subgroup N of G is normal if for all A and N and G and G, I can conjugate A by G, which means the following thing. It's called the conjugate of A. This guy, whatever it is, it has to be also in N. So we denote, if this subgroup satisfies this property, we denote this. We put a triangle here. That denotes normality. Normal subgroup. But no, so observe, kernel satisfies this property. Kernel of a homomorphism satisfies this property. For any homomorphism. D. A is in the kernel. Then if I take a conjugate of A, this is equal to this guy. By this last lemma we have. But if A is in the kernel, phi of A is 1 on G prime. So I'm just multiplying something with its inverse and I get 1. So kernels are normal subgroups. And in some sense, that's sort of a defining property of a normal subgroup. They can be kernels, but we'll get to that later. All right. I thought this would take like about 10 minutes. It took most of the class. So let me, I would like in the last 5-6 minutes to explain something about isomorphisms. Isomorphisms are homomorphisms that are one-to-one onto. So bijective homomorphisms. And you read about these, this means that they have an inverse, I mean, because they're bijective, they have an inverse function. And there's a theorem, an easily proven theorem in the book, a lemma or something, that says that that inverse is also a homomorphism. So they are not, they're functions that have homomorphisms with inverse homomorphisms. And so I copy over, I made this little figure to explain something about isomorphisms. Isomorphisms are something we can really understand, I think. Homomorphisms are slightly more complicated, actually. Isomorphisms, they have this, they basically say that two groups have the same basic structure. And so I put in, I drew up the multiplication tables for two groups. I took the permutation group 3 numbers, 1, 2, 3, and I drew up this morning, early morning, drew up this little table, multiplication table, composing permutations. This just says, okay, if I've got a permutation P here and a permutation Q in this column, what is PQ, right? I just combine them and I, so, 1, 2 times, or well, I guess let's do here. So 2, 3 times 1, 3 is 1, 2, 3. So you can think of, go back to elementary school for a moment. Think of building multiplication tables, but now you have a log composition table. You can draw this whole thing up. Not hard to do. There's another group called the dihedral group. A very nice group. We'll learn a little more about it. It's the group of symmetries of some regular polygon. Okay. In this case, D3, and also sometimes called D6, depending on the geometer or algebraist. This is the group of isometries or symmetries, if you will, of an equilateral triangle. So what can we do with an equilateral triangle? Well, we can reflect across sort of one of these axes. Or we can rotate it, by like 120 degrees. Or we can rotate it the other way by 120 degrees. And those, or we can leave it alone. That gives us 6 symmetries of this triangle. And if we compose symmetries, we can reflect and then rotate, or we reflect and reflect. We can do this, those form a group, those operations form a group. We can build this multiplication table of that group as well. This tells us how to compose symmetries. Now it turns out these two groups, while they certainly, you go to someone on the street and say, okay, one group is, permuting bijective functions. The other group is symmetries of D3. While they are defined in different ways, they are in fact isomorphic groups, meaning they have the same basic algebraic structure. And it's not hard to see why.
Is D3 commutative?
D3 is not commutative. D3 is not commutative. Let's just see why. Let's say, well, what we can do is, if you trust my multiplication table, which you shouldn't do because I was still drinking my first cup of coffee, I made it, you will see, let's take R1 times R2. I get row 2. I get a rotation counterclockwise or clockwise of 120 degrees. If I go R2 times R1, I get row 1. So if you want commutativity, this whole diagram should be symmetric about the diagram. The whole multiplication table should be. So this one is not. Moreover, I can see something. If I trust this, I can see something. I want to say that I can make an isomorphism. And the way I'm going to make an isomorphism, I may go a little bit over, but I won't go too much over, is I can color. My favorite thing to do. Right around when my daughter was waking up. She's like, what are you doing, Dad? I was coloring. And I said, I'm coloring. She said, oh, that's fun. We need breakfast. I said, fine. I can color, right? And I can color also the columns here. And this will give me a map from S3 to D3. And I just say, okay, I map things of the same color to each other. And I'm going to ask, is this an isomorphism? Is this an isomorphism? Well, for this to be an isomorphism, it means that if I use this color code and I fill in the entire table, I'll get the exact same color picture on both sides. That means that the multiplication is compatible with that assignment of elements. So let's just check for green. I've got green here. So I've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So now my green over here is a row 1. So I go row 1, row 1, row 1, row 1, row 1, row 1. I get the same position, right, of the greens. So isomorphism means equal shape, right? And this is like the shape, you should think of your table as the shape of your composition. Right? And this is just, if you have an isomorphism, it says, okay, I may have labeled these elements differently, but they really are combining in the same way. And that's what an isomorphism is telling us. And in that sense, it gives us a better notion of what it means to be the same group than just saying strict equality. Okay. Okay. All right, guys, I'll see you on Wednesday.